Costa Rica, nice. UK, great. Monterey, I'll be up there in a couple days. Fantastic. South Carolina, Miami, nice. Louisiana, lovely. Okay, Washington State, love it. That's great.
All over.
Supposedly we have a couple people coming in from Switzerland. And a couple from Australia here. I don't think they're up yet. Bahamas, welcome. Hi, Joe from UK, that's great. Wow, you guys are up late. And Maine, yeah, I'll be up there also pretty soon. Nice, Seattle, I love it.
All right. We are ready to go, Dan. Should we go ahead and get started?
Yeah, let's kick this off.
All right. Well, hello everybody. My name's Leo Adams. I'm the co-founder of Skylink, a drone community and professional services marketplace. I just want to thank everybody for hopping on our call today on our training, and definitely excited to be here with you guys and have the opportunity to present to you guys the first of our four-part training based on drone-based LiDAR. And we hope you find this information helpful in whatever line of work you are. But before we get started, I want to go ahead and just take care of a couple housekeeping things. So first, if you guys have any questions throughout the webinar, feel free to, on the bottom of your webinar screen, you'll see the Q&A section. Go ahead and type in your question in there. We'll definitely be monitoring those questions and, trying to answer all of those towards the end of the webinar. Feel free to use the chat function as well, for general messages. You can definitely ask questions in there as well, but we'll definitely be, taking the Q&A questions first. And if we don't get to all your questions, we, again, are having a second part webinar in 2 weeks. So definitely hold on to those questions and answer them there, but we'll definitely do our best to get those answered.
I'll probably make a couple videos for the ones that we don't and send them out direct to them. So we'll get them answered for them, for sure.
Perfect. And I know we sent over a link in the welcome email, a link to a LiDAR prep course, just some pre-webinar information we thought might be helpful for you guys to see and absorb pre-webinar. We know the link might not have been working, so you'll see the corrected link there at the bottom, modus-ai.com/what-is-LiDAR. So feel free to check that out. If some of the stuff Dan starts talking about is going over your head, that link will definitely, provide some good information and help you grasp some of these concepts better. But with that said, I'd like to go ahead and introduce you to the panelists today. We have Tom Hess, who is a MODUS team member. He'll be helping us moderate the Q&A in the chat room. And of course, Dan, he's the owner of MODUS, 20-year aviation and mapping expert. Currently working with companies on integrating photo and LiDAR mapping solutions into their business architecture. And, he works also with commercial and government agencies on defining safe beyond visual line of sight mapping operations. So we definitely want to thank Dan for hopping on our call today and, sharing his expertise. So thanks, Dan.
Excellent. Yeah. Hey, everybody. Thanks. We'll kick this off really quickly here. But first off, thank you for attending. Obviously, everybody here has some kind of interest in LiDAR, whether you're doing it in your business now or you're looking to explore this. And what MODUS really does is provide business solutions. So we're not manufacturers. We work with a lot of manufacturers, but what we do is enable companies to evaluate the technology, look at how that business case works for them, implement in some kind of pilot program in the field, and then refine that process so that you're profitable and lean. So that's what we do in MODUS, whether we're doing sales, rentals, training, or if you're in some of our research projects, because we're involved in a bunch of IPPs, beyond line of sight type of technology, stuff like that. So that's kind of the core of what we do. So I'm glad that you're here, and for me, the rules here today are to show you a little bit of a hint of what LiDAR can do. It usually takes us hours to get a basic person up to speed, so we're not going to be able to do all of that today. We're going to touch the top surface That's what we're doing 4 of these. And if you'll notice that we're going to actually have more of these beyond that. But first, we want to get through the basics and then take it from there. So some upcoming events that we have going on. We'll have, again, who are the customers coming up in 2 weeks. 2 weeks after that, we'll get into the drone LiDAR equipment. So, how to actually evaluate that equipment in terms of return on investment. Not, hey, I'm going to sell you this box, or let's use this one. What actually makes business sense. And then we'll wrap up this 4-part series with best practices. So when you're planning your jobs, what are the things you want to consider? And then we'll get into our premium series, which will get into more specifics on workflow. Whether you're doing stuff in utilities, we'll look at some of those use cases. We'll look at stuff in the construction industry, and we'll look at stuff in the infrastructure industry. And then also, if you guys are aware, we'll also have some live events coming up that you guys can talk to us about. So this is all our training series, and with much more to do, we'll move forward here. So, the first thing I want to talk about, I'm not going to go through this whole entire slide, but the first thing is that, drone-based LiDAR is not the end-all, be-all. You have tons and tons of solutions that are out there, and depending on what your case is, there's a lot of times that when I'm doing pre-work for a client, I'm actually going to look at satellite imagery, even though it's only a few points per meter squared. It's enough to get a project going. Or if I'm doing flight automation, I may do a LiDAR cloud from satellite first in order to set up my topography so that I know where the ground is. So satellite has a definite place to be. And right now, with the current laws that we have today, whether you're in Europe, Canada, Mexico, or here in the US, if you're going to cover a wide area, aerial is going to be. Where the drone niche actually fits in, and where we're starting to see this actually start to happen, is in small areas. So you're looking at anything up to about 100 to 300 acres right now. It's back of the truck equipment, so it's ease of use. But we're not going to see the full capability of what the drone can do until we get beyond the line of sight, and that's why MODUS is aligned there. In addition, you have mobile, so a lot of our sensors and a lot of other people's sensors will go from drone to car, and that allows a lot of extra functionality, especially when you're working around airports and you don't want to deal with Atlantic or any of those kind of restrictions. And then, of course, you'll have the terrestrial, and we got done with a study where we did drone and mobile LiDAR versus terrestrial LiDAR. There you go. And obviously the terrestrial did better. Let's say for a site that we were working on, I think it was only like 3 acres. It took them about 2 hours to complete that with the terrestrial. Great resolution. These were crime scenes that we were doing. In contrast, we did the whole site up to about 3 centimeters of resolution in 3 minutes. So there's a case for a drone setup, and there's a case for terrestrial. And if I had to have high detailed for imagery, terrestrial would be a case. But if I needed to get something done quickly into a certain data specification, then you'd be looking at a drone. So here we just wanted to sum up that you have options, but really what we want to get into is the components, because this is part of what the training series is, just to kind of get you introduced. And the reason why I'm bringing this as part of the training, if you guys already know, please forgive me, is that I would say 50% of the clients that come in and ask about LiDAR and look at the cost and what's actually involved don't fully understand all the technology that is wrapped up into an integration. So especially colleges that they're looking in the pricing on the Riegl website or the Quantity website or the Velodyne website, the LiDAR head is just the beginning portion of this. And that's great if you're doing terrestrial and you can sit in a constant space. But in addition to this, you're going to have your GPS, and some units use 1 and some people use 2, and that has to do a lot with the inertial navigation system. And then the heart of this, and really when you're dealing with mobile applications, your IMU is going to be everything, and we'll talk about that in just a second. You have data recorders you're also going to have in here, and probably the biggest thing is, what kind of correction are you going to use? If you're using a terrestrial sensor, you can sit still, you can have just a GPS antenna, and you can make those kind of corrections the longer you sit there. But when you're moving, you're going to actually have to weed out a lot of that inertial movement, atmospheric type of conditions, a lot of error that goes along with you actually moving from one spot and your reference plane changing. So with that, like I said, the inertial navigation unit is really the heart of the system and what makes a mobile unit actually work. What you have going on here is, or what makes the inertial navigation system is the, first off, the GPS antenna on top. And that's going to dictate how much error you're going to have and how quickly you're going to be able to, sample the constellations. In addition to that, as part of that GPS antenna is what kind of receivers are you going to be using? And so you have half a dozen different constellations, whether you're using the US model, which is just straight GPS, GLONASS for the Russians. You can have Galileo, NA for the Chinese. And a lot of what I do is actually use multiple constellations to help with that refinement. In addition, you're going to have refinements. So some people that are familiar are going to have an L1 and an L2 signal. L5 is coming out, even though we're not seeing any of our equipment come up to speed on that yet. And all our customers aren't seeing that for their ground-based measuring units. But that's also on the, whether you're doing anti-spoofing or you're doing anti-correct, or not anti-correction, but regular correction, having receivers that have that that additional carrier signal to refine that atmospheric interference is pretty important. So that's one of the things that you're going to want to look in that GPS receiver is how robust and how much correction is actually happening in real time. The other part of the inertial navigation unit is going to be the IMU, or the inertial measurement unit. And this piece of that is, it can be either electrical mechanical, so a MEMS chip, which are getting better and better, or you can be sitting with some type of gyro. And the advantage of what we're seeing, especially now, like most drones, all drones that are in the small commercial market are using chips. And we're seeing that actually being more and more refined as the technology matures. So that's the advantage of that. One of the ways that we've seen a lot of clients go now is to, instead of using a fiber optic gyro, which helps in pitch roll and specifically heading, some of the manufacturers now are using a dual GPS antenna setup. And again, it really depends on what the specs are and what their software is going to be and the sampling rates. But a dual GPS antenna, oddly enough, isn't getting you twice the GPS signal. It's getting you a GPS location on one antenna, and it's getting you pointer information. And what that allows the system to do is refine heading a lot quicker. So if you're flying really tight spaces, a dual system may be something that you want to look at. With that said, the farther apart those two antennas are, the better refinement you're going to get. So a lot of the folks that are doing this are going to have to separate their antennas by about 2 meters or more. In a small UAS market, when you're flying in confined spaces, at least for my personal opinion, that gets kind of challenging, where a lot of these people are putting it low. It makes your landings difficult, your landing sites more difficult. So I'm not a big proponent of it, but when you look at the telemetry data or what's actually happening, and we'll talk a lot more about this in the workflow at the end of this webinar, it definitely gets back onto heading very quickly, and that allows your whole solution to be just a little bit better firmed up. Some of the systems we use a higher refresh rate and post sampling to make it better. With that said, the other ways to look at this is some other considerations we're going to want to look at is, how are we calibrating and how much are those refresh times? So this is getting back into specifically that MEMS chip. how fast is that actually sampling inertial change in the X, Y, and Z, and then what kind of rolls it's doing. Something we didn't talk about a second ago, but we'll bring in now is, in addition to having this GPS capability, and in addition to having this inertial capability, when you're dealing with motion, whether you're dealing it with on a drone or you're dealing with, especially on mobile applications, is what's your loss rate? And the way these systems actually work is your GPS is going to be probably on a 1 second or maybe a half a second pulse, finding its position. And normally that wouldn't be too bad, except for, your LiDAR is actually sampling at hundredths of a second. But as far as like actually knowing where the drone is, it's usually not too bad. You're not going to get a lot of lapse rate, but depending on where you are, if you're in a city application or you're behind a hill, you get a lot of interference, you may lose GPS signal. Where this becomes much more important is when you're dealing with mobile applications where you're driving and you're going through, let's say, a tunnel. At that point, the IMU's ability to fill in the gaps between a GPS hit 1 second and a GPS hit 40 seconds from now may be important. And so one of the things you need to consider when you're looking at the INS solution is, how long can you go without a GPS signal and still maintain heading? So that's something that, just a little tidbit to take a look at. And again, like I said, for drones, it's not as critical, but I have had times when I was flying and I've lost 30 seconds of GPS time for whatever reason. Where in some of the mobile applications, I've had to go up to 40, 45 seconds to get through a tunnel. So again, that's really important to understand, like that time duration, and also to understand what that really does to your GPS position and heading. So a lot of the manufacturers, when you look at this and you're looking at their spec sheet, they're going to tell you what the lost time is, and they're going to tell you how far the heading will degrade in that time. So that's something you should look at on your spec sheets. Excuse me. And the last thing with an INS, a lot of the INSs are actually tied to software support. And there's some folks that actually have made their own. And so you really kind of need to take a look at how that software, what's that software actually doing? I mean, don't get into the code or anything like that. But what I mean is, depending on what your application is. So if you're in, let's say, virtual reality up in Hollywood and you're doing FX type of productions, at that point, you having a very accurate point cloud on the Earth's surface is probably not as important as getting a really good image. But however, if you are a surveyor, an engineer, and you're laying out topography or grids, or you're doing structure deformation where we're actually putting one point cloud on top of the other, and that registration is going to be really important as we measure the changes that are actually happening. So depending on your use case and how stringent your data has to be, geospatially speaking, really is going to dictate what kind of software you're going to want to use. And so my typical advice is to go with some of the bigger folks, whether you're looking at PostPack and Trimble or Hexagon, Inertial Explorer. I think there's a couple others out there. And the reason being is they're going to come into corrective services. So some will use the National Geospatial System, where whether it's CORS or OPUS, and they're using all the remote survey stations to help geo-level your position. Some like Riegl and some of these guys have their own constellations that you can tie into. OmniStar, I think, is one of them. That may help depending on the resolution that you're working. And this will get your GPS solution down to 2 to 3 centimeters, and then we'll do the rest with inertial. So again, looking at that software support and the correction service is going to be important. The last little bit of this on that software support is most sensors are going to pick up in UTM, but most surveyors are going to be using some kind of plane system or something local. So they're going to have a very specific datum and ellipsoid they're going to be going off of. And so being able to convert between different grids and datums is kind of important from what we've been doing over the last 3 years as you try to transform your data from one measurement standard to another. So again, that's another reason you need to look at that software package and make sure that it really is survey grade if you're going to be doing geospatial mapping. Okay, so that's the inertial unit. And if that wasn't enough, how are we on time here? Looking good. Okay, so the next piece of this is the other part of the equation is the LiDAR sensor. So while the IMU or the INS solution is going to be really driving your absolute accuracy, which we'll talk about in a minute, the LiDAR sensor characteristics are going to drive the relative accuracy. These are the pictures that everybody sees on LinkedIn or on LiDAR News or something like that. We're like, ooh, wow, that's great. And so the things we need to look at here when we're looking at LiDAR heads, again, and by the way, before I get into all this, every one of these here are good for an application. It depends on what you're actually trying to achieve, or more importantly, what does your customer need? So before I go diving in and saying, well, this one's great, and that one's great, they're all good. It just really depends on what you need. I mean, 90% of what I need to do, I can do with a Velodyne VLP16. But there are definitely applications that we have worked with customers for where the full Vox HA was required. But the difference in price is like tenfold. So just understand that you can buy a big hammer, but you may not necessarily need it. Excuse me. So the first thing that you want to look at is relative accuracy when we look at a LiDAR head. And relative accuracy, you know, a lot of folks will put it on their spec sheet, you know, and sometimes you'll see, oh, it's 2 centimeters or it's 3 centimeters or it's 10 millimeters. You really want to see that relative accuracy established with a range. And the reason being is, you know, whether you're talking about certain amount of deemed divergence or you're talking about angular error of the spinning head, with time, or I'm sorry, with distance, these areas get bigger, and the area of uncertainty that point gets bigger. And that's what relative accuracy is what is one point in reference to another and how accurate is that? And that's what causes an image. Also, there's some time of flight sensors. So the way these sensors work, if you haven't attended the online course yet, is a LiDAR pulse is sent out, or a light pulse is sent out. And it's timed from the time that it leaves the sensor to the time that it reflects and comes back and strikes the sensor again. So depending on which sensor you're looking at down here, there are going to be different sensitivities on how well it actually times that time of flight of a packet of photons as it goes and bounces off a wall or bounces off an object and comes back. So like I know some of our vendors are actually tuning these sensors because they're automotive sensors in some of these cases, and they're not designed to be, or at least the factory doesn't send them out to be mapping instruments, and we have to do the further engineering and the further calibration to make those work, or at least to be reliable every time. So that's relative accuracy and the things that you need to look on the spec sheet. The next thing you need to look at is the intensities. So what intensity means is, you know, you're sending out a pulse and you're going to get a light shift when it reflects back. And that's going to dictate, especially like with road scan, when you're hitting, let's say the road, black tar is going to be 100% absorbent, or pretty darn close. But the white reflective lines on the road, and I'll show examples in later webinars when we go through some of the use cases, you can start to see strip matching or strips. You can start to see different types of features based on how much light's reflected. It becomes really important when we're starting to do analysis so that we can, you know, a lot of folks see the point clouds where we use height coloring models, which we use, you know, red, blue, green, depending on how high or what the elevation is. But we can also adjust the gates of the intensity to start measuring that. And believe it or not, that's actually color information. So we can false color a point cloud to actually generate an image. It's a lot of work. You need special software, but that helps with, especially with vegetation management, or when you're picking out infrastructure, especially small refined features. Using the intensity views can help an analyst really pull out those classification features. So again, understanding how much intensity that each one of these sensors have, is important depending on how robust your application is going to be. The next one is range, and this is pretty self-evident. Again, when we look at, let's say, a VLP16 or a 32, you're looking at really a max range of 80 meters, and that's from the sensor to the target. If you're flying, you have to actually take into account side scan and that kind of thing. But we cover that in our planning course, and I think we'll touch on that. I think on the last training that we're going to be doing. But again, range dictates one, how much you can see and how much area you're going to cover in a period of time. And that range, when you start to look at this and we start to pull out point density charts, that range is going to dictate how much point density that you're going to have. So, the more robust sensors, you may have a different curve than, let's say, an automotive survey grade sensor. Then the next piece here is, so you have pulse repetition frequency, or we like to try to simplify it down to points per second. So depending on which sensor you're looking at, the VLP16, I think is 250,000. The HCL32, we're looking at 800,000. The M8 is 400,000. The mini bucks is, I think, 150,000. And I have forgotten what the bucks is. It's been a little while. Why that's important? Depending on, so if you're doing, let's say, survey operations, a lot of surveyors, if you're only doing, let's say, 2-foot contours or 1-foot contours, you may only need like 8 points per meter square or 16 points per meter square of return. However, if you're dealing with vegetation and you're trying to get penetration, it really comes down to how much energy is put out and how much is actually reflected for the characteristic that you want. So I'm going to use Velodyne as an example here really quick, where we have 16 sensors and 32 sensors putting out energy. So 250 versus 800,000 on one return. Each of these are going to strike, let's say, grass, but who has a higher probability of actually making it through the grass? Probably the 32 from what we've seen on the data sets. So how much poke through is going to be part of the function of how many points per second that you can actually put out. So that's, and another use case would be, in the particular case, like let's say this forensic study we just did, is how much detail are you actually going to get? So if you're doing like feature extraction of buildings and you want very refined detail, the amount of points per second, which is a PRF function and a couple other things, it's going to be very important because you want the image versus actually trying to get some kind of topography. I'll get to ground control points there, Rich. That's a very important question. You're kind of beating me to the punch. So let's get through the technology and I'll get there for sure. The next part is returns. So returns, what this allows, again, in the basic course, returns is, when a piece of light actually hits an object, part of it scatters, part of it is returned. And depending on how it hits, some of it may actually still continue on and hit something else and reflect. And so depending on the sensitivity of the sensor, certain sensors can actually pick up 50% or 30% or even 19% of the original signature. And so we set up gates and use that to actually pick up more structure on one light pulse. Why is that important? Again, it depends on the application that you're trying to achieve. If you're doing, let's say, volumetrics in bare earth, you just need one return. You'll get a solution within 20 minutes if you're just doing volumetrics. once you start getting into vegetation penetration, that's when you want to start looking at returns. If you're just doing, like, let's say canopy height modeling, probably one return is going to be fine. If you're going to start looking at actual structure, then you want to start looking at 2, 3, and 5. So if you're starting, like, let's say you're doing forestry, and you need to start figuring yield rates of the trunks and how much biomass, then you're going to want to look at 3, 4, and 5 returns, which some of these sensors have. And then finally, the last thing I'm going to talk about here is track record. Some of these sensors, like I was talking about, they come out and they've been designed to be security models, automotive models, and they're not really designed for mapping. So, really take a look at, what the literature is saying and how some of these are performing. Take a look at the point clouds and really evaluate, and then go through a workflow and see if they're just cleaning it up or, what actually is happening with those clouds. But again, like, for instance, Riegl has an impeccable track record. They're designed for surveyors. Even their literature and their specs are very conservative to what they actually do, versus some of the others that boast overclaims on their capabilities. So this is kind of that buyer beware, to really do your research and make sure that you're buying the best unit in the class of sensor that you need for your business.
Hey, Dan, I'll just jump in here. We had a question, I think, that, want to just go ahead and throw out there. So from Sam, is points per second directly correlated to the density of the resultant point cloud? Obviously, the points per second is related to the LiDAR sensor, as Tom mentioned in the Q&A, but can we expect higher points per second of that LiDAR sensor to result in, more detailed point clouds?
That's a good question. So what I'm talking about, points per second, or the PRMF, is the amount of energy that's going to be sent out. Now, we have to talk about returns, and this is a little deeper. So I'm only going to touch on it, and we'll talk about it more in detail when we talk about planning and that kind of thing. But every object has an albedos, and an albedos is a reflectivity based on the spectrum of light that you're dealing with. And so you'll see in the literature or the spec sheets, they'll say, hey, it's 80% return, or it's 40% return, or it's 18% return. And that has to do with the color signature. So, like, for instance, if you're dealing with black, you're going to get something like a 5% return. And so, like, when we look at hot pavement or hot asphalt on a roof in the summertime, we're getting virtually nothing in returns for those points. Water, and the same thing, has no return. So it doesn't matter how many points per second I send to it, I'm not going to see an image. Conversely, if I have white dotted reflective paint, I'm getting close to 100% return. Typically, if we're talking about, like, brown earth, we're talking about 75 to 80% return. If you're talking about vegetation, you're looking at, let's say, first tier green vegetation, we're looking at maybe 25% return. These are ballpark figures, but you have to understand that the more experience you get, the more you get used to going, okay, well, I know I have vegetation and I'm going to have to either go slower or lower, or I need to change the sensor that I'm using. But the first place you have to start is, how much energy my sensor can put out and how much energy can it detect back. So that's the first place we start. Does that help there, Leo?
Yeah, I think so. Thanks, Dan.
And if you want more, put it in the chat, and then we'll see if we can, or I don't see anything in the Q&A here yet, but put those in there and we'll try to address those later on, because I really do want you guys to have this information. It's going to really benefit you guys later. All right. So I did say I was going to talk about levels of accuracy. And the first thing I want to kind of demystify, because what we see in the market is, hey, look at all this relative all this accuracy. I'm getting within 3 millimeters of accuracy. Well, I'm sorry, there's very few sensors on the planet that is going to get you 3 millimeters of geospatial accuracy unless you're doing some phenomenal things, especially with a mobile sensor. And so what they're really talking about is the relative accuracy. So we're going to look at two things here, just hopefully kind of spell this out. And again, the online course we have hopefully breaks it out a little bit too. So the first thing is relative accuracy, like we talked about, is the relational accuracy between points. And so what we have here, this was a recent study we did in Kansas last week. It almost killed me. You know, and so you can see everything here is pretty crisp. This is within 3 centimeters or 30 millimeters, maybe even a little bit better. And the software is going to tell you what the distance spreads are going to be. And then we used terrestrial laser scanner scale. So in the center here, if you can see my mouse, you have these little triangles. And so whoever asked me about ground control points, this is the first step of ground control points. So we use this ground control point not for geospatial accuracy, but instead for relative accuracy. So we have, this was measured down to 3 millimeters using both RDK and geo-leveling techniques, which is, we took a bunch of different stations and we had to cross-fix and do some crazy surveying stuff to get the resolution down to this little point to be within 3 millimeters. And then we have a measurement in between these two. We also have some strip bars, but I don't have a good picture of those, that also were used to go, okay, the distance between this white ball and this white ball are within 1.27 meters. So that's what we use for relative accuracy, and that's where that type of control comes into play. Also, just for, so I don't forget it, because there was a question on control, these points are also used to register your data. So the terrestrial scanning data and our drone-based data were actually fused together in another part of the project. And you do that by using control points to level your clouds out. We call that registration. So hopefully that kind of makes it clear, you know, what relative accuracy is. And so, like for instance, back here where you see this mound of dirt, you know, all I need is relative accuracy to get the volumetrics. I don't need positional. But here, when we're talking about these points, these control points, now I'm talking about absolute, which brings us over to this other picture here. So this was a study, 3 weeks ago for Caltrans, and we're still working it. But you have some imagery here, and this was also done with a VLP sensor. And so this is a 4 foot by 4 foot control point. And this is where intensity comes in. So we have pure black, and you can see how little return we have here. And we have reflective pure white, and you can see how many points you have here. And so we're using this to actually establish how much error there is between the LiDAR points that have hit here and the survey points. So that's what absolute accuracy is a definition of, I know on the Earth's surface exactly where this point is in X, Y, and Z. And my sensor is reporting that it's, let's say, 3 centimeters off. First off, you can correct for that afterwards if you know what it is. But that is making it, you know, relation to the Earth's surface or established reference grid. Along with that is, shoot, I just lost my train of thought. But also here, I'm going to show you another sensor, and this is actually a pyramid. And so we can also use shapes, curves, and other features to use to identify for control, to actually make sure everything matches. Oh, that brings me back to the last point. So getting back to it, so while we talk about the error between one point and the actual measurement that you've done, you know, when you're dealing with surveyors or you're dealing with data standards, now you need to do some statistics to go, okay, well, I have 12 points out on the field today. And so I need to figure out whether either statistically I'm within 95%. So that's a statistical measured under a bell curve to go, you know, I'm within a certain percentage of all my points. So therefore, this cloud is within a certain percentage of accuracy. Root mean squared is another method. But again, what you're doing is you're summing up all these points. You can look at each point and go, okay, I'm off by, let's say, 10 millimeters. And I'm off over here by 12 millimeters. But then when you look at them all in aggregate, that is going to get your your root mean square error. And that you can use in a global transformation of your data to reduce the offset even more. So that's where ground control kind of comes into play in that piece. So hopefully that further refines that, and we'll talk more about control in the workflow here in a minute. Okay, and we did, I'm not going to go into a lot of detail here. I think I've already beaten it down, but for accuracy, we talked about it when we talked about the components. Your first part of your accuracy is going to be your LiDAR, and how well that sensor, but that's going to be mostly your relative accuracy. The other part is going to be your inertial, and this is the part that kind of throws a lot of people off, is when you're moving, you're going to pick up errors, whether it's GPS errors, bias, and acceleration errors. And so having good software, having good components helps refine that. And this, I promise you later on, this will when we tie it into workflow, this is going to make more sense in actually how we derive a solution. But the INS is largely what's going to be responsible for your absolute accuracy. So hopefully this is just a couple second splash, but hopefully this makes some sense here. All right, now levels of accuracy. So we talked a little bit about inertial and and that type of for that absolute accuracy. But there's different levels that we can talk about. So you can do autonomous, which is on the slide. So that's using the L1 and the L2, and that will get you within probably 1 meter. If you don't even use the L2, you're going to be within, I think, 10 meters. So that's your cell phone, that's working off cell towers and GPS signals. With a corrected, now you're in the aviation grade. That's what that was originally designed for, where you're doing base station correction from the national grid. So that's taking the satellite, and that's taking a base station or a ground station to geo-correct and then send all that to the GPS receiver. So that's your autonomous solution. Now, what precise point positioning is, if you're not familiar, at least in the US, I'm not sure what's in the UK, but I can look that up really quick. And I know that Australia doesn't have much of this either. But this is just using an established set of survey points or survey stations. So like in California, really kind of blessed that every 20 kilometers or so, I have a survey station that's actually giving telemetry data 24/7. And so we use those stations. Oh, and then back up, then you're in Kansas where there was absolutely nothing for 200 kilometers. But we use those stations to try fix the GPS point that we have and make a correction to it. Because the Earth is, you have the error in common for the constellation, and then you have errors due to the location that you're on the Earth, whether it's magnetic or gravity, or there's a bunch of different errors that go into that. So that's the first level of correction. And again, it depends on the GPS of the day and a lot of things to actually refine. So I'm not going to give you any numbers on what that's going to get you. The next piece is post-kinematic and real-time kinematic processing. And so what that does is it's very similar to point positioning, except now you're bringing your own equipment out and you're getting it close to the area of capture. So if I'm doing road scan, I may set up a network of base stations that are collecting and maybe even reporting on a radio, which would make it real-time kinematic. And what I'm going to do is I'm going to take now the GPS signal that I'm receiving on my drone or my car, called the rover, to the base station, and I'm going to compare these two. And any of the error that they have in common, we get rid of, because that's common error. And that allows us to refine the accuracy in or the accuracy of that motion.
Hey, Dan, I think along the same lines, we have a question that kind of relates. So for achieving absolute accuracy with ground control points, there's two components. There's the positional survey GPS part of the GSP, ground control point, and then there's the intensity panel part of the ground control point. Is that correct?
Yes, for LiDAR, that is correct. It's going to be different for photogrammetry, where You can use spectrum data or color data, but for LiDAR, it's intensity data. That's correct. Okay. So moving on here to this, now there's on the market, we have folks that are really strongly in the real-time kinematic, and we have some folks that are really strong in the post-kinematic. And the only difference would be in how the data is sampled. Real-time kinematic is a base station of the radio that's talking directly to your drone or your mobile data. So it's making geospatial corrections in real time. The downside to that, if there is that you're only going to sample a very finite amount of that error. So, and I'm not sure what that is. It depends on, again, the software that you're going to use, but let's say 20 seconds. You're only going to look at 20 seconds of positional data and then make a correction. And so you're constantly making these small samples. Where post-kinematic, you download the base station data and you download the rover data, and then you put it through a service, and what you do there is you sample the entire constellation feed from both rover and base station, and you can move forward and back 2 or 3 times to do leveling adjustments. So you'll get a better solution than PPK. It just takes a little bit longer. So it's a matter of preference. Again, look at the specs and go look at the data. But for me, for what I do, trying to get the best accuracy geospatially, I tend to go to PPK. But it's not that you can't use RDK for your solutions. Again, it just depends on what your customer needs. Now, we talked a little bit about control points. So a control point correction, depending on what vendor you're using, could be, you actually plug those points in and you can use manual correction. Some of the software we use actually uses a proprietary sampling method. So we declare where it is. We have the LiDAR tool look in that area within, let's say, 20 meters, find it, and then sample the amount of points of reflectivity and do, again, another root mean square adjustment. And for that, what control points typically does for you is removes most, not all, but most of that inertial error. So typically in our workflow processes that I do, I'll do a PPP. I don't even do a PPK if I'm going to do ground control. And then I'll throw ground control in and get rid of all that error. And so all I'm left with, in theory, depending again how good I'm processing and how thorough I am with my numbers and my ground field support, I'm just left with the relative error of the sensor. But again, the amount of effort that you're going to have to do ground point correction, especially if you're doing it at scale, is on par with photogrammetry at that point. And again, for the surveyors and the engineers and those folks, your most refined point or your most accurate point is going to be a survey point that you've not just done RTK with with a rover, but actually geo-leveled. Okay, that's the most accurate point that you can have out there. So it's very important for surveyors to understand that LiDAR will fill in the gaps and will get you your contours, but you're still going to have to go out into the field and survey those key points that you're going to want to turn into your customer. So LiDAR is an augmentation tool, not a replacement tool like a lot of people think it is. So I'm hopefully clear on the amount of accuracy that we have here. Does that work for everybody? Okay, workflow, all right. And we're doing pretty good with time. Sorry, I'm a little over, but we'll get there. So workflow, this is a long drawn out process of everything that's involved. The items that are in gray are really outside of what I want to talk about, because what I'm going to talk about for workflow is really the acquire, post-flight, or what I like to call compile in the post-processing to achieve a geospatially corrected point cloud. So a little bit different than scanning where you just get a point cloud. And so what you have here, for pre-planning, this is your bidding process. This is like somebody sending me CAD drawings. And for some of the software we use, we take that and we load it into our mission planner to assist with, setting up our job sites. But then when you start to talk about mission planning, which is our course that we usually teach for our rentals and for our sales, Now you start looking at, what kind of flight, what kind of profile, what kind of overlaps do I need to ensure collection? Do I need 10% overlap? Do I need 30% of overlap? Do I need to do straight, or do I need to do cross grid? This all goes into the mission planning. And then, as we talked about here, where do I need to set up my control? I mean, just slapping down a few control points doesn't work. You need to really start to use either ASPERS or USGS standards to set your controls into place so that you can validate your data. And then you have your emergency accident plan and risk mitigation plans and all the things that you would need if you're a professional drone operator that's going to work in a high risk environment. Then you get into the acquire, and the acquire is frankly pretty straightforward. You have your automation that you'd load in, or your mobile tracking, and then you'd be controlling your LiDAR unit, whether you have to do a raw or a coarse calibration as part of that, or however that is actually set up. Excuse me. So the acquire, again, is pretty straightforward. I'm not going to go into detail on how do we do that. I mean, I teach a whole separate course on how to fly and take into account terrain and all of that. And I think I have a couple webinars I can share with everybody that we put out on advanced flight automation. But really, the big piece of where the magic actually happens is in the compiler or the post-flight. So depending on what system you're using, you may have it streamed, you may have it downloaded. A lot of the systems that we use, we just literally use a USB 3 high capacity, high speed thumb drive, and which allows us to literally land, pull it off the bird, and start processing right there on the field. Some have some kind of streaming where they'll stream down partial images. Oh, by the way, if you see folks showing you like, hey, this is streaming in real time, it's probably a downsampled or done in post-processing for marketing. Everything that I've seen usually takes like maybe a 2% or a 3% of the cloud, and that's valuable, definitely for tracking your progress. But I would say it's a nice to have, not a need to have. But again, that's there for you. But then for there, you also will download your telemetry data off your base station if you choose to do that, or you'll upload data from one of your subscription services to do the PPP we had talked about. From there, we'll come in and we'll do a telemetry correction, which I'll show you here. I'll show you some pictures of that in just a second. And then we do the compiling. And so what compiling is we take the corrected trajectory information. So that's the path that your vehicle has gone or your drone has gone. And that's usually sampled down to the hundredths of a second for your position. And that is fused with the LiDAR information that's also sampled and is on the same clock sync. And that's going to fuse in whether it's, what sensor head, what angle. There's about 27 different data attributes that are linked in between the positional data and the LiDAR information. We can cover that more in detail later if you want, or you can look at the ASPER standards and they'll show you, what that LiDAR data should look like. And then we'll do some kind of quick filtering usually, and that's your post-processing. So this will get you your first LiDAR cloud. And then to do some post-processing, and this gets confusing depending on who you're talking to on these terms, but for me, post-processing is now the data conditioning. And that's when we start looking at the actual point cloud. We're no longer looking at the raw data, and we're clipping it. So that means we're trimming off, whether I'm wanting to look at side scan or I'm looking at mapping data. So I'm going to clip it for what I need. I'm going to clean it, which means sometimes I'll get false returns underneath or above. So I'll clean out any of the stray noise that I may have, and that varies from sensor to sensor and atmospheric conditions. This is where I probably would colorize. So if I have imagery, this is where I'm going to do draping. Some people call it rubber banding. So instead of doing photogrammetry where I'm processing for and have to have a server, I can actually take the image and drape it over and add color to the LiDAR point cloud, which is one of those 27 attributes we talked about. Actually, it's 3. It's red, blue, green. And then I'm going to register my data. So I'm going to take those control points and I'm going to make sure that it can be used with other data samples, you know, of the same set. And the last thing I'm going to do is I'm going to make sure that my metadata is right. The metadata is important because it tells you, well, again, it's an ASPR standard, but you know, who took this, where was it done, what time was it done, what grid, probably the biggest thing, what geospatial grid are you using? You know, are you using UTM and WSG84? Are you using NADS 83? Forgot what the new standard that's coming out next year. Because if you don't get that right, you could see offsets. Well, I've seen 12-foot offsets and I've seen 100-mile offsets. So making sure that you have the right grid is going to be important. And a lot of times the data that we see that a customer comes back to us and goes, this is totally off, means that they looked usually at the wrong, they opened it and declared it the wrong grid. You know, for the error that you should see is, you know, you could be a couple centimeters off, but if you're in the magnitude of feet, you better take a look at your grids. And that's where that metadata comes in. And then later on, when we talk about use case, we'll talk about classification schemes and how do we manipulate that data. But for the purpose of this course today, what I really want to say is that this is where the money is. This, when we look at mission planning, acquiring, compiling, and processing, this is kind of like photogrammetry. You can do it really, really quickly. You know, you're going to spend a lot of your time in setup, so that's where you set up your control points and laying out your plan. That's where you're going to spend your time. You know, a typical a typical 20-acre flight, doing a high accuracy or high density collected, like 5 meters per second, takes me 15 minutes, something like that. And I can go faster if I want to. So the flight time, you know, is really, really quick. It's going to be your setup time. That's going to take time. So like talking to the surveyor, finding that point, figuring out where your base station is really supposed to go. That's, you know, when you talk about an acquirer and you're trying to set up field operations, that's where you're going to spend your time. But the real value is in the data. And this is what is kind of hurting the industry right now, is a lot of folks do not know how to process and analyze this data. Even folks that are using point cloud information right now, they don't know how to do transformations. They don't know how to manipulate this data to actually get products. And so for the folks that are looking at this, you know, we spend about 25% of the time talking about acquire, and we'll spend 90% of the time talking about analyze, and making sure that whatever the data spec here in the deliver is in the planning process so that you can achieve it. So that's our secret sauce there, guys. We always ask what the data spec is before we even start planning or recommending a sensor. And so if you ever sit down with us, that's the first thing we're going to ask you is, what's your spec? And, you know, construction companies, utility companies, engineering companies, a lot of times won't know. They'll say, well, you tell us what it's supposed to be. And that's where you're going to have to get out and sample and really know your customer and what their data products are going to be. I've been through enough utility companies to go, oh yeah, this is what it's, yeah, you just tell us what it's going to be. Or I've got a surveyor that does that for us. And not knowing your data spec changes this whole workflow and the amount of time that you have to collect. It's amazing. So again, we'll talk a lot about analyze in some of the use cases and stuff like that. You know, and then the other place that is maturing right now is how you deliver it. You know, whether you're going to give them some customers, honest to God, we get all this way, get all the way through, and we deliver a two-dimensional drawing because they just want paper. Other folks want us to put a CD in the mail because they're worried about cybersecurity. And other people use Dropbox and we drop, or we'll use a three-dimensional point cloud viewer, you know, before we do final delivery. So understanding that data management and upload, and this takes a lot of time actually. And some of these clouds, after they're processed, take a lot of effort to move up and down and across the net. All right, and so I'm going to leave you with the last bit is what data format. So in LiDAR, you're going to have, your LAS formats where you can have an XYZ, lat long, or, you can get it into an Esri. So this is the starting point. And this is what I was talking about in the analyze phase is how are you going to deliver that information? What does your customer need? Because every time you process across here, you're going to add a little bit of error. It just happens. So making sure that you understand and work with your customer to tell, okay, you're going to have this amount of accuracy here. This is the key deliverable. And then what product am I going to deliver that helps you make a good business decision and helps you make or save money? So that's my final point that I'm going to leave you there for this training. Let me see if there's anything here.
Thanks, Dan. We actually have a question.
Okay.
In regards to, obviously, the analyze phase is a key component of the workflow. Do you have any recommended tools for doing the analytics, or what would be your suggestions there?
Well, there's tons, and I can recommend software that's $20,000 a year, and I can recommend software that's free, and obviously you're going to get what you pay for. So if you like Bentley or you like Esri, those are great. I'm starting to really like a Cyclone for certain aspects, but I'll tell you that there is no software out there right now that is the Swiss Army knife for LiDAR. Okay, you can look at Harris and NVDI, they're all good for certain aspects. And so we'll talk in some later training on different workflows. And that's part of what I do as a business is I look at what the existing workflow of a company is. So whether you're a traditional inspection company or you're a surveying company, and then I look at what you do traditionally, and then I mirror up, depending on what the metrics of success that we establish are going to be, to what that workflow would be to achieve those results. So if you need to speed up, if you have a training component, or you have a ease of use that you need, or you have a very specific product that you're trying to deliver, that tailors what software actually shows up in that workflow. But I'm not going to tell this group here that, hey, you got to run out and get Bentley because that's the absolute best, because we probably have sampled 25, 30 different LiDAR and photogrammetry pieces of software. And in our workflow, I'll tell you, I'll process in one piece of software and I actually view in another piece of software. And that's just been the nature of the beast. So that's something that, I can go into more detail, when we work on an actual project or something like that.
Yeah, and we'll obviously, our next training in 2 weeks is going to be obviously on know your customers, understanding some of those use cases and getting a better feel for who are the customers that need LiDAR and drone-based LiDAR services. So we'll dive deeper into that.
Okay. So, obviously we have another event coming up. I didn't put the date earlier on, so it's going to be on the 24th, and we already have the registration page for that. So for those folks that thought this was useful, would like to dive more into the use cases and maybe get a little more specific on how we're going to use this for different industries, we have that coming up in 2 weeks. And then the last offer is more, like I said, I showed in the beginning, we have a hands-on component. We've trained all over the place for large companies and and for these group offerings, because we know this is an emerging field. And so we have a partnership with Kansas State University on the small UAS range out there where we're their commercial LiDAR partner. And so Kansas City, we're going to have a one-day course where you're actually going to get to fly, you're going to get to talk or deal with let's say the base workflow that we carry. We'll have 2 different vendors there to show these technologies, both in mobile and in aerial. You will actually physically do some of the workflow, and we'll talk more about some of those analytics. And then if you do a course like this, you do also end up with 2 hours of free consulting with me, which typically, we start off at 350 and the second hour hits 1,500 an hour. So, I give that as free because you've done the initial investment and I want you to be successful. So if this is something that is interesting to you, or you're like, yeah, I'd like to delve this in. This here is 500. We normally do 800 for this. But down the bottom corner, the bit.ly LiDAR course will get you to the Kansas State registration page. And so again, if this is something that you're like, okay, I'd like to get some hands-on time with our analysts and LiDAR experts, this is a great way to get some exposure. So, and